Hello everybody. In this little extra video segment here, I thought I'd give you a more advanced way that we can also motivate a different formula for mean curvature. This is a formula that I think doesn't typically show up in undergraduate differential geometry classes and is reserved for kind of a more advanced setting, but it actually is really important in the applied universe. So I thought I would kind of show you where it came from in at least an informal proof. Moreover, this allows us to practice variational calculus, which is everybody's least favorite computational tool in 6838. Okay, so here's going to be our basic setup here. So the basic idea is going to be that we're going to have a time-varying sequence of surfaces, right? So like a surface that's somehow morphing over time. And the question that we want to answer is, what is the rate of change of the surface area of that surface as a function of time, right? That kind of sounds like what we've already talked about in the universe of variational calculus, and indeed, essentially, this is another excuse for us to compute a Gâteau derivative. So here's the way that we're going to do it. We're going to assume that we have a time-varying sequence of surface patches. So we're going to say a sequence of surface patches. And we're going to assume that they're parametrized by a particular function, which we'll say is ft of u comma v, which is going to go from some region u in the plane into 3D. Okay, so let's draw a picture of what we mean so far. So here is the plane. So there's u direction and the v direction. And we have some region here, which is big U. And essentially, we're going to have a map ft, which goes from this patch in the plane into some part of a 3D surface. Remember that we call surfaces M in this class. So here's a M. And M is embedded in R3, so this notation is perfectly fine. In particular, there's some region here which is like f of u. Okay? So we don't need to worry about tracing out the entire surface, just some little patch on it. That's going to be good enough. Incidentally, this is a little u and a big U, in case you were wondering, but we're not going to need either one very much, so I'm not going to worry about redundancy here. Okay, so here's going to be the question, which is, if I insert a little bump on my surface, right, my surface grows a little tumor, and I can think of that tumor as growing as a function of time. The question is, can I figure out how the surface area changes in response to that? Okay, so we're going to make a few different definitions to make our life a little bit easier. And in particular, these things are going to basically tell us about the direction of motion of our little tumor as it grows, in addition to the tangents of the surface, the normal, and so on. Incidentally, I'm going to apologize in advance. I've got my handwritten notes sitting right next to the screen here. I'm going to be looking down a lot because this is a bit of an involved calculation. And I hope you guys bear with me, even if I'm not looking directly into the camera here. Okay, so in any event, if I'm at some point, the first thing that I always seem to define in this course are tangent vectors. Those are just generally useful. So in particular, let's define a tangent vector in the u and the v direction. So I'm going to write tu is equal to the partial derivative in u, and tv is equal to the partial derivative of ft in v. And I'm actually going to define a third vector as well. Incidentally, these are also functions of time t, but I haven't written it here. Hopefully you guys can follow. I'm going to define a third vector, and this is one that I want to make sure that you guys understand. And that I'm going to call wt. And I'm going to say that this is equal to the partial derivative of f in t. Okay, so remember, so I want to make sure that we're 100% clear on the role of these three vectors. Okay, so remember our basic setup here. We have ft for each time t is parametrizing a patch on our surface, and then t is essentially, controlling the surface as it evolves. So these two guys are tangent vectors, like maybe this is tu and this is tv, and then we have a third vector which says I'm going to stand at a point and look at its velocity as the surface changes, right? So if the surface is growing a bump like that, so I have maybe at time 0 it's like a little bit bumpy, and then at time 1 it's like more bumpy. So here's t equals 0, there's t equals 1. Then the WT vector is going to look like that, right? So I'm standing at a point, and I'm figuring out where that point moves as time moves forward. Okay, so these are 3 useful vectors. Essentially, by equality of mixed partials, or also just by definition, we can write a few identities that are kind of convenient. So in particular, let's write the following. So here's some identities. We know that essentially, if we look at the dtu in time, right? So if you think about it, that's differentiating f once in time and once in u, right? Then I could have swapped which ones I differentiated first, and so essentially that's the same as dwt du. Right, because really, both of these things are just differentiating f once in time and once in u, and there's equality in mixed partials. Similarly, I can say dtv in time is equal to the derivative of wt in v. And right, there's one third thing, which is I can differentiate tu in v and tv in u, and both of those are the same thing because they're just the mixed partials of f in the u and v directions. So in other words, I can write the following, that the derivative of tu in v is equal to the derivative of tv in u. If these expressions are confusing, that's totally understandable because they all look the same. So I would encourage you to pause this video for a minute and make sure that you can derive each of these from the definitions here and just what f of t is to begin with. And really, you'll see that all this is just equality of mixed partials. I'm just making lots of definitions, partially for convenience and partially because these are nice geometric things, right? Like capital Tu and Tv are 2 different tangent directions, and then W is the direction that a point is moving as my surface evolves. So I can think of W in particular at t equals 0. That's what we're going to do at the end of the day. I can think of W0 as a vector field on my surface, right? So like if I've got my torus, there he is, and it's growing a little bump here, then I'll have a vector field, which is essentially the direction of growth of the bump sitting somewhere. So if we think of area as a function that goes from surface into a real number, right? For every surface, there is a surface area. Then essentially, the computation that we're going to want to do today is to look at the derivative of area in the W0 direction. So this is the derivative of area at the surface M in the W0 direction. Now, if you go back to, I guess, lecture 2 in this course, then this is essentially a Gateau derivative, right? Essentially what I'm saying is, what is the rate of change of the surface area of my surface M as I deform it along the vector field W at time 0? Okay, so that's the object that we're after. And we're going to see that it basically only depends on W0. It's not going to depend on the derivatives of W in time, which is a good thing. And that this is a really famous formula, and one that's going to come back a few times in this course. First when we talk about mean curvature, like we're doing now, and then later when we talk about the Laplacian operator. So this is one of these ones that we might as well really explore in some detail. Okay, so what we're going to do is, rather than looking at the area of the entire surface, that's a little complicated because maybe I need multiple patches to cover the whole surface and parameterize with this f. What I'm going to assume, just for convenience, this is a convenience for 6838. If you were taking a real differential geometry class, you go back and patch this up later. But just for simplicity, we're going to make an assumption here. My apologies, this marker is falling apart here. We're going to assume that essentially Wt is identically equal to 0 outside ft of u. And in fact, maybe even along the boundary of ft. So essentially the point here is that our deformation is really small. It's just inside of this region here. And the reason that I'm doing that is that when I differentiate surface area then, it's sufficient to differentiate the surface area of the image of u because nothing interesting is happening outside of there, right? Essentially, there's no velocity to my surface except just an itty-bitty bump that I'm adding inside of that patch. You might say, Justin, is this kosher? And the answer is absolutely not. But in 6838, our main goal is to give you an intuition for these kinds of calculations rather than the full formal one. So I'm going to make my life a little easier. You know, assume makes a something or other out of you and me here. Okay, so the first thing that we can do is remember how we take ghetto derivatives. We essentially say, okay, we're going to think of area as a function of time, differentiate it, and then evaluate it at t equals 0. Okay, so our first task here is to write area as a function of time. And now that's not so difficult. Let me change markers. Okay, so here is area, and it's a function of time as our surface evolves. And hopefully you all remember from your multivariable calculus class the following formula, which is the area of the image of u ends up looking like the double integral over u, but I'm going to omit that subscript just because I'm lazy, of the following, which is the cross product of dft du cross product dft dv, and then I take the 2 norm of that and I integrate with respect to du dv. And this is integrated over u. So that's the area of the patch that is parametrized by our function f. If you don't recall that formula, I'll defer to your undergrad calculus class to kind of review this one a bit. But it's just the cross product of the 2 partial derivatives. And recall that we gave these guys names, right? So this is big T sub u, and this guy here is big T sub v. Okay, so essentially what we're going to do for the remainder of this video, but it's going to get kind of painful, is we're going to differentiate A with respect to time t. Okay, so everybody buckle your seatbelts and get ready. Let's go for it here. Okay, so we're going to say, what is A prime of t? This is also going to be a great test of my board skill here, which I admit is extremely poor. So I'm likely to run out of space a million times and have to pause and erase, and I apologize in advance. Okay, so remember by differentiating under the integral, this integral is over u and v, and I'm differentiating in t. So the derivative of the integral is the same as the integral of the derivative. I can write the following. D over dt of this cross product. I'll write tu cross product tv. Okay, so far this wasn't terribly complicated. Now we have a derivative of a norm formula. I'm going to allow you guys to work it out on scrap paper. But essentially when I differentiate the norm of a vector, I get a factor of 1 over that vector times the derivative of what's on the inside. I believe that we actually kind of justified that a few lectures ago. So we can write that this is equal to the following. It's the double integral. I'm going to omit the subscript u just to save space on the board here. Of, let's see, the norm of tu cross tv to the minus 1. And now this thing gets multiplied by what's in the inside, and then by the chain rule we have to dot product that with the derivative. So now we get tu cross tv dot product the derivative of this object, d over dt of tu cross tv. I know this one went by a little bit fast, but this is a 1 variable calculus exercise, so I'm going to allow you to double check this one at home. When I say allow, what I mean is that your instructor is being lazy. Okay, so our next step here is to apply the product rule in this term here to expand it out. And moreover, just to compress things a little bit, we can observe the following, which is what is tu cross tv? Well, maybe I'm going to define the orientation of my surface, like the normal direction, as this cross product, right? Notice that these are 2 different tangent vectors getting multiplied together in a cross product. Remember, the cross product is mutually orthogonal, and it's divided by its norm. So this entire expression here is nothing more than the unit normal to my surface at that point. So that's kind of nice. So now we can collapse things into n and apply the product rule here. And what we get is that this is the double integral of n dot product the following thing, which is the partial derivative of tu dt cross product tv plus tu cross product the partial derivative of tv with respect to time. Okay, so we're starting to get some slightly cleaner notation here. And let's see if we can make it even nicer. And in particular, what we're going to do is notice that these expressions here, right, these derivatives in time, have alternative expressions based on our mixed partial identities that we wrote farther up on our board. Namely, du dt is equal to a derivative of w, and dt, d tangent vector in the v direction dt, well, this thing is also a derivative of w. Now, why am I doing this? Like, what kind of intelligent design do I have that leads me to think that's the right next step in my simplification? Essentially, at the end of the day, what I'm going to want is the rate of change of area really in terms of w, right? Because that's like the velocity of the surface as it moves around. So I want to get rid of as many of these tangential terms as I can. Okay, so let's do that. In particular, this is equal to the double integral of the normal to the surface dot product. So we have dtu dt, which is here, right? So this is the same as dwt du, cross product with tv, plus tu cross product, and now we have this other derivative, dwt dv. Okay, and this is integrated again. So now we're getting somewhere. We have an expression that looks quite different from what we started with, which is pretty good. But we're still not done, unfortunately for us. Now, we're going to make use of one other little kind of useful formula. This is something called the triple product identity. I'm going to move my notes over here. And the triple product identity can be written as follows, and this is just something you can check algebraically. Essentially, the triple product identity, maybe I'll just hold my notes, tells us the following, which is that in general, if I have A dot B cross C, parenthesized that way, for vectors A, B, and C in 3D, this is equal to B dot C cross A, okay? So this is another one of these expressions that you may remember from pre-calculus class. You might have to double check on your scrap paper, but I think I'm confident that all of you guys could check this one at home. Now, why did I write this little formula down? This is called a triple product identity. I'd write it down, but I'm out of space. Triple product identity. Well, take a look at our expression down here. We have the normal dot cross product. And so essentially what the triple product identity is telling me is that I can cyclically permute the things that are inside of a triple product without affecting the value. Okay, so let's do that. We're going to continue our simplification of A prime. Maybe I'll section things off on the board a little bit. Let's see if I can follow the screen here. Okay, so yeah, so now what do we have? Well, we're going to cycle these things around. And what I'm going to try and do is pull out the derivatives with respect to u and v to the outside, because that's what's going to allow us to apply integration by parts. Okay, so at the end of the day, what do I get? I get that this is equal to the double integral. And now I'm going to pull the dwt du to the outside. So I'll get dwt du dot product. I have to cyclically permute, so it's, let's see, tv cross n. Okay, and I'll do the same thing for the second term, but now I'm going to cyclically permute it twice, right? So I will get plus dwt dv, and this is dot producted against what? Well, I kind of have to read it in a cycle, n cross tu. Okay, and now I check my notes and I make sure I'm right. N cross tu. Okay, and so this is integrated again over our patch. Whew. Okay, so now we're going to do a few things. I keep saying that. This is a complicated calculation. I apologize. I don't apologize. It is what it is. Now, in particular, we're integrating over the region U, and we made a convenient assumption because your instructor is lazy, which is that W is identically 0 outside of this region, and in fact, maybe even along the boundary as well. So what does that allow us to do? It allows us to integrate by parts with impunity and ignore boundary terms, which is good because I never get the boundary terms right. So let's see here. What can I do? Well, notice that this is kind of like the gradient, right? Like this is dwt du and dwt dv, dot product with some other terms here. So when I integrate by parts, what's going to happen is that I'll move the derivative off of these terms and onto the other ones. This is something that requires really staring at and getting right. But essentially, by integrating by parts, what we're going to get, there's no boundary terms. So it's like boundary term minus another integral. But instead, we just get minus the double integral of, we're going to move the derivatives off of the w's and onto the other terms. So we'll have wt dot product. Now we get a bunch of terms in the inside. You're going to get d over du of tv cross n. Yep. Plus d over dv of n cross tu. So this is just integrate by parts in the multivariable sense. This is a byproduct of Stokes' theorem, if you recall that one from your calculus class. And in general, just when I say integration by parts in 838, what it's saying is I have it's kind of like a fancy souped up version of the product rule. I have the integral of the derivative of an object times another one, and that's equal to boundary terms minus the integral of the first thing times the derivative of the other one. That rule is almost always true in some version or another. So you just have to look up that Wikipedia page of integration by parts formulas, and you'll find this one on there somewhere. And essentially, this is just integration by parts on this two-dimensional UV domain here, with the additional assumption that nothing interesting happens to our function f along the boundary of U. I warned you guys this calculation was a bit involved, and indeed, I think you're seeing that now. It's about to get more so. Okay, so our next task is to simplify this expression inside of parentheses here. So in order to do that, what we're going to do is apply the product rule to both of these terms. So I'm going to call this thing star. And now we're going to simplify star a little bit. So let's just follow our nose here. We'll follow the Toucan Sam approach to mathematics. So if we apply the product rule to the first term, we get the partial derivative of tv in u cross product with n plus tv cross product the partial derivative of n in u. And now let's differentiate the second term here. So we're going to get dn dv cross product tu. And then finally, we'll get n cross product dtu dv. Okay, so that's just the product rule. And now we can do all kinds of different simplifications here. Now, in particular, of course, if I flip the order of a dot product, it changes sign. Right? So in particular, I'm tempted to erase with my finger, but that's going to smear everywhere. So that's equal to the first term plus the second term plus the third term minus dtu dv cross n. And now here's kind of an interesting thing. I have dtu cross n, dtu tv cross n, and I've got dtv du cross n with opposite sign in front of each other. But take a look. So we have this convenient little identity right here, again from mixed partial derivatives, that the derivative in the v direction of tu is equal to the derivative in the u direction of tv. So in fact, these two derivatives are equal to one another, meaning that they cancel. So in other words, that starred expression is just equal to the sum of the two middle terms. Okay, it's just equal to tv v cross product dn du plus dn dv cross product tu. Okay, so now we've simplified this expression inside of our area integral. So let's go back. I'm also going to swap the order of this cross product and put a minus sign here. So in other words, what do I get? I get that a prime of t is equal to, well, I can return to this integral here, and now I'm going to sub in this expression. So I get that this is the double integral of w, oh no. That could have been worse. Of wt dot product this expression here. So we have tv cross product dn du minus tu cross product dn dv. Okay, du dv. So now we're getting somewhere. We're quite close. Actually, I probably shouldn't have swapped this order, but that's okay. We'll just fix it in our next row. Okay, so now we're going to start introducing a language that looks like our curvature computation. In particular, notice that this object here, this is the shape operator, right? This is the derivative of the unit normal in the u direction, right? So I can write this expression in yet another way. This is the double integral, oops, there should be a minus sign, minus the double integral of wt dot product. And now what I'm going to say is that this is tv cross product, the shape operator in the tu direction, right? Because it's the derivative of the normal vector in the tu direction. And I'm sorry, I'm going to undo my cross product here. And I'm actually going to write, well, how do I want to write this? I'm sorry, I'm looking at my notes. So this is dn. Oh, I'm sorry. No, I'm going to leave this this thing here and say that, okay, this is minus tu cross product dn of tv du dv. Okay. Now, notice there's a minus sign on the outside, so I can swap these two terms here and get rid of it if I wanted to. Okay, so here's an interesting observation. So in general, let's think about what all these objects are. So we have this thing here. Well, remember that this is the shape operator. So this is actually in the tangent space of our surface, right? Remember, we proved that in our main lecture on curvature here. And similarly, for this term here, this is a tangent vector. Okay, and tu and tv are tangent vectors by definition. So what does that tell us? Well, we have the cross product of two different tangent vectors in each of these terms. So actually, they're both parallel to the unit normal to our surface. They're both parallel to this n vector here. Okay, so to repeat myself here, tu and dn of tv are both tangent vectors, so the cross product is normal. Similarly for this first term. So these are just some scalar multiple of the unit normal of my surface. So one thing that I could do is say, okay, well, if these guys are parallel to the unit normal, then any component of W in the tangent plane to my surface actually doesn't matter. Do you see that? Because it's getting dot producted with some multiple of n. So at the end of the day, when I follow all of this logic, what this means is that I can write kind of an interesting expression for my double integral. So this is equal to the double integral, and I'm just going to take the normal component of WT, because the tangential component doesn't matter. So this is really WT dot product the normal. And I'm going to take the normal component of this other expression here. So here's how I can do that. So I'm going to move the minus sign inside and swap these two terms. So this is TU cross product dn of TV minus TV cross product dn of TU. So this entire expression, I'm just going to take the normal component, because we know that this is parallel to the normal anyway, so I somehow haven't really done anything. Du dv. Okay, so now we're cooking with gas. In particular, we should look at these expressions. You know, I could move this dot product with the normal to the inside and kind of figure out what's going on. Yeah? And one thing that you can convince yourself quite easily is that actually all this is doing is giving us an expression for mean curvature. How do I see that? So in particular, this is equal to n dot the cross product of Tu and dn of v here, and so on. Pardon me. And so what is this thing? Well, this is a vector in the n direction whose length is equal to what? The length of this guy times the length of this guy, which is just 1 times sine of the angle between them, right? That's the definition of cross product. Now, if I took Tu, so let's see if I can draw a picture of what this is doing. So I have some point, and here is Tu, and here is dn of TV. Remember that this is a tangent vector. N of TV, like that. Okay, and I'm going to make one more assumption that I can always do on my functions. I'm going to do it for convenience. I'm going to go backward a little bit. And I'm going to make one assumption for convenience. I'm going to assume that Tu dot TV is equal to 0. So in other words, I'm just going to choose a parameterization where the two coordinate directions move 90 degrees to each other. So in that case, what's going to end up happening? I have Tu like this, and I've got TV, which is some vector 90 degrees to Tu like that. So it turns out, this is just a trigonometric fact, that the norm of the cross product between these two vectors, if I rotate Tu by 90 degrees, it's going to give me the norm of the dot product between the other two guys. That's a little bit complicated, but essentially what this is telling us is that really, what is this expression here? Well, essentially what I'm going to end up getting is the following. Well, I'm going to have the directional curvature in the u and the v directions. So I'm going to get this. Now, the reason that this minus becomes a plus has to do with the orientation of the cross product relative to the orientation of our dot product. Like we keep multiplying by moving things by 90 degrees. I know that I kind of talked in circles around that fact, so you should convince yourself that this is true at home. Like that. Okay. But the basic point here is that I made an additional assumption that Tu and TV are orthogonal. That's actually something that I can always do for my function ft by just kind of pre-composing it with a matrix that takes what might be two non-orthogonal directions and stretches them out. I'll let you convince yourself of that at home. And essentially what I'm doing is just using properties of cross products and dot products to say that, like, okay, tu cross dn of tv is like tv dot dn of tv, because these things are rotated 90 degrees off of one another. I know that sounds a little circular. I'll let you think about it at home. But if you're willing to trust me there, then finally we end up with a nice expression, which is the following. Well, essentially, I can take this term, which is just 2 times the mean curvature of my surface, and I'm going to factor it by putting that mean curvature in front of this normal here. So this is the second derivative of the dot product between wt and the normal to my surface weighted by mean curvature. Now, if this explanation sounded a little fuzzy, that's because it was. I would encourage you all to take a look. I did this calculation in detail in the course notes, and you can read it there. But let's step back and see what we did before I erase all this, clean it up, and give you a nice, tidy interpretation. So essentially, if you recall, we started with a surface, and we said we're going to allow it to grow a bump as a function of time. And that bump is going to be concentrated in the interior of this region U. Or really f of u, I guess. And we said we're going to look at area as a function of time. So this is just the usual area formula for a patch that's parametrized by some function f of uv. And I just differentiated with respect to t by moving it under the integral. All the calculations all the way up to here are just standard calculus. There's really nothing complicated involving the integrals at all. In fact, I can get all the way to this point by just using mixed partial derivatives and a few other definitions that we wrote here. Then we integrated by parts. Essentially, our goal was to move the u and v derivatives off of w and onto these cross product terms. And that is what yielded us this expression here. We simplified the internal thing that was dot producted against w, and that led us to this new expression downstairs. And then essentially by just a little bit more algebra about cross products and dot products, we ended up in the following expression. Do I expect all of you guys to be able to reconstruct this? Obviously not, since I was lecturing with my notes the whole time. But I do think that it's useful to know the basic strategy, which is I wanted to take the variation of area along some vector field wt. So I wrote area as a function of time, where to first order the way that my surface changed was by moving along my vector field w. I computed this first derivative. At some point later on, I integrated by parts. That almost always happens in variational calculus. That's what led me to my expression here. And I did more and more simplification until I ended up with this nice result. Okay, so hopefully we all at least got the high-level points here. I'm sorry, I'm hiding behind the board. Let me do a little bit of erasing, and then we're going to talk about how to interpret this expression and why it's useful in your everyday life. Oops, I'm missing a factor of 2 here. I apologize. Okay, so let's pause and erase. Okay, that's better. So I've just collapsed all of our simplification. And again, what did we show? We showed we have a time-varying region on a surface. If we take the derivative of surface area in time, we end up with 2 times the integral of mean curvature against the direction of motion of the surface. So a kind of tidier way of writing the same thing is that we took the Gaussian derivative of area in this vector field w direction, and we got 2 times the integral. I'm going to cheat and say over our surface. We didn't actually argue that, but like a sort of partition of unity argument gets you there. Of wt dot product, the mean curvature, normal, d area. Now, I haven't really defined what it means to take a surface integral, but I do think we understand this expression here. So right, so what are we really saying? So remember from lecture 2 in this course that if I had a function f and he went from Rn into R, and I computed df at x0 in some vector direction v, we showed that this was equal to the gradient of f evaluated at x0 dot product with v. Okay, so this was like our little finite dimensional picture that we're going to keep in mind. So take a look at this expression. Well, now we took the derivative of area of a surface in a vector field direction, right? So remember our little schematic. We took the surface and we put a little field living on the surface telling us how the surface is changing. And we got the dot product between the direction of motion of our surface, oops, there shouldn't be a t there, and the mean curvature normal. So this thing is kind of like the gradient of surface area. And in fact, it turns out that this is a really great analogy. Now remember that this is a mean curvature weighted normal is a vector field on a surface, but indeed you can think of it as the direction to flow to increase surface area. So as a very simple example, think about the sphere, maybe even a radius r if you want. So there's the normal directions, right? They point outward. And that makes sense because remember that the gradient is the direction to move a function to increase the value of the function the most. That's, remember, gradient descent, the algorithm goes down minus the gradient. So gradient ascent, like moving along the gradient, makes a function bigger. And indeed, the mean curvature normal of a sphere, well, it's in the normal direction, so it points outward. Essentially what it's telling you is if you want to make a sphere bigger, displace the sphere along its surface normal. In fact, one kind of interesting thing is that, of course, that scales in a particular way with the radius of the sphere because the curvature of the sphere decreases as the radius increases, which is something I'll let you kind of work out the asymptotics of at home. Okay, so in fact, there exists an extremely famous partial differential equation, which is called mean curvature flow. This is an advanced kind of Google search term thing rather than something we're going to define carefully in this class, which takes points on the surface and flows them in this, it kind of does gradient descent on surface area. So it looks like this. By the way, we're not too concerned with that 2 factor. That doesn't really matter here. So the idea of mean curvature flow is it takes a surface and it tries to flow the geometry along the mean curvature weighted unit normal direction. And essentially you can think of it as gradient descent on surface area. And so this gives us sort of an interesting interpretation of the mean curvature. Essentially the mean curvature is telling us something about how successful we can be at changing surface area by flowing in the unit normal direction. So for instance, the mean curvature of a plane ends up being 0. That's not terribly surprising since the plane is flat. And here that makes sense because essentially there's no direction to first order I can flow a plane to decrease its surface area. It's a minimal surface. And in general, when this mean curvature flow converges, then I end up with a particular type of surface called a minimal surface. And minimal surfaces are actually encountered in our everyday life because they're bubbles. So in particular, if I take a piece of wire and I cut out some shape, unfortunately this is hard to draw in 3D, but I allow the surface area, so I stretch a surface over this piece of wire, and I decrease the surface area the most while keeping that wire in some fixed shape, then the surface that I'll get is a minimal surface, and it essentially is trying to minimize by flowing along this gradient direction here, subject in this case to Dirichlet boundary conditions, meaning that the geometry of the outer ring of the circle is fixed by that piece of wire. So in any event, for now in our course, this is going to just suggest a different way that we could get mean curvature out of a surface by essentially differentiating area in some fashion and then seeing what comes out, which is going to be the mean curvature weighted normal vector. So what we're going to do in our next lecture, we're going to say, okay, well, a triangulated surface like this has some area function, right? So now area you can think of as a function that takes in the coordinates of all the vertices, right? So there's 3 coordinates for each vertex, and gives back a real number, in fact a positive one. Well, I can take the gradient of this function, and now this is the honest to goodness gradient, right? This is basically saying I can move each of these vertices around and affect the areas of the triangles, where now area is just equal to the sum over the triangles t of the area of each triangle. So in this case, what we're going to end up with is a mean curvature weighted normal, just interpreted in the discrete domain. So for instance, think about like if I have a, I don't know, a ring of vertices, and then I've got one vertex kind of pointing up like that. So this vertex, I'm going to actually draw a pyramid. And I take the gradient of area with respect to this vertex here, well, what's it going to want to do? Well, if I take the gradient of area, that's the direction I can move this vertex to increase curvature the most. It's going to give me some direction like that, which looks an awful lot like a normal vector at this vertex. So this is actually a way to define vertex normals for a triangle mesh, and it's a way to, if I take the norm of that gradient, it's a way to get some approximation of mean curvature, at least up to sine. So we're going to pursue that perspective in our next lecture, but for now, I encourage you guys to go back through the course notes and review this calculation. I know it went by a little bit quickly, but the basic point here is that we can think of there being a vector field on a surface, which is the mean curvature weighted normal, as being a gradient of surface area, meaning the direction I can flow the surface to increase the area the most. And we got there by differentiating this expression that you probably have seen in undergrad calculus class and doing lots and lots of annoying calculations. So with that, I'll see you in our next class.